I had a good day to our IRTS Dr. Faisal bin Mama. Today we are going to present about our mini project that is title of ground improvement using PVD with the preloading. Okay, before I will into our mini project, I want to introduce ourselves. I am Lohindan son of Parmeswaran and our team members are Nisa Manjuri Arumugam and Nur Sabrina binti Ahmad Mukris. And then the first we are going to see in this mini project presentation is introduction. Okay, what the introduction for our mini project? Construction on soft marine clay is a major challenge in the geotechnical engineering. Soft marine clay has a high compressibility and low shear strength, which make it unsuitable for supporting heavy structures such as highway embankments. If construction is carried out without any ground improvement problems such as excessive settlement, cracking, and even failure may occur. Therefore, ground improvement techniques are necessary to ensure safety, stability, and long-term performance of the structure. Okay, next we are going to what is our problem statement. Okay, let's see our this is our image of the problem statement. So, in our project, we are consider her eye embankment constructed on approximately 10 meters of the soft marine clay. This type of soil has high water content and very low permeability, meaning water drains very slowly. Because of this natural concentration, may take many years. This can lead to uneven settlement, slope instability, and also structural damages, which is unacceptable for highway construction. Hence, an effective ground improvement method is required. So, this is our problem statement. Let's we are into the objectives of our mini projects. Okay, what are our objectives? The objectives of this project are several. First, we aim to understand the behavior of soft marine clay under embankment loading. Next, we want to demonstrate how fabrical vertical drains, that is PVD, combined with the preloading can accelerate concentration. We are also aim to show improvement in soil strength after the construction. In addition, we are construct her 3D model, integrate geotechnical instruments and the related theoretical knowledge to real engineering practice. So, what is our scope of the project? The scope of our project begins with studying the characteristic of the soft marine clay. Then we identify the problem and propose PVD with the preloading as the solution. Next, we are design and build a demonstration model, install PVD and monitoring instruments and explain the construction process. Finally, the project is completed with a technical report and presentation. This project focuses on conceptual understanding and demonstration rather than the detailed numerical designs. And next, we are going to see the main part of this mini project is our proposed solution. What is our proper solution is for this project you are using probable vertical drains, that is PVD, combined with our preloading, and PVDs are installed vertically and throughout the soft clay layer while a temporary preload embankment is applied on top. The preload increases pressure in the soil, forcing poor water to drain out throughout the PVDs. This process accelerates concentration, increase effective thrust, and improve soil strength before the actual service load is applied. Okay, that's we are see our 3D model. This is our 3D model. We are using Revit and will do. This is the image of our front view, how it will be if we have apply load. We have three method, that is settlement plate, piezometer, and also the inclometer. These are the instrument we are going to use. Let's we are see the simulations video. This video shows a simulation of ground improvement using fabrical vertical drains (PVD) combined with the preloading for a highway emet construct on soft marine clay. Let's we are see our sound. This is our sound of water that the water will be observed by the PVDs. At the beginning of this simulation, the exciting ground condition is shown. The soil layer represents soft marine clay which has higher water content, low shear strength, and very low permeability at this stage. The soil is weak and unable to support heavy loading safely. Next, the simulations show that installation of pebblical vertical drains, the PVDs are installed vertically throughout the soft clay layer extending from the ground surface. To the bottom of the clay, these drains act an artificial drainage pads, shortening and the poor water needs to travel during concentration. After the PVD installation, a preloading embankment is applied on top of the ground. This preload increases the total stress in the soil and generates excess poor water pressure within the clay layer. As the time progresses in this simulation, we can see that poor water begins flow horizontally towards the PVDs and then vertically upwards to the ground surface. This process represents the accelerated concentration which is occurs much faster than natural concentration without PVD. The video also demonstrates settlement of the hammer. Most of the settlement occurs during the preloading stage, which is stable because it allows settlement to take place before the actual service load is applied. At the same time, as poor water pressure dissipates, that effective stress in the soil increases. This leads an increase in the soil strength and stiffness, improving overall ground stability. Finally, the simulation show a stable ground condition after concentration is completed at this stage. The preload can be removed and the soil is strong enough to support the permanent structure with reduced long-term settlement and improved safety. One line closing for our mini project of this 3D modeling. The simulations clearly demonstrate how PVD with preloading accelerates concentration, reduce settlement, and improve the strength of soft marine clay in accordance with the concentration theory and real engineering practice. This about our 3D modeling. Let's we are going see the why PVD with preloading. PVD with preloading is chosen because it improves the soil in situ without the need of excavation of soil replacement in shortened than drainage paths. It's faster concentration compared to national project and is suitable for high-end infrastructure projects. This also cost-effective and widely used method. And lastly, we are going to before the last we are going to see the soft marine clay characteristic because the soft marine clay is a play a big role in this mini project. Soft marine clay has several unfavorable properties. It has a high nature water content which leads to large settlement under the loads. Its low permeability causes slow drainage while low shear strength increase the risk of failure. In addition, the soil is highly compressible, meaning settlement can continue for a long period. Because of these characteristics, ground improvement is achieved before the construction. Last but not least, you are going to see the effective stress concept. What are our effective stress concept? Total stress applied by the embankment load and is transferred to initial stress carried by the poor water pressure. After that, water drains are gradually over time and soil becomes denser and stronger. And last, the effective stress are increases. That's all from me. Next will be continued by our group members and thank you so much.
Hi, Assalamualaikum. My name is Nur Savina and I'm gonna explain to you about consolidation process. Since soil has tiny space between its particles and those spaces are often filled with water, what we call pore water, when we put a heavy load on the soil gets squeezed and the water drains out. Because of the water lift, the soil particle will move closer so that the soil volume becomes smaller. In soft clay, consolidation occurs two stages. Primary consolidation begins after loading. Since soft clay has low permeability, so water drainage takes slow. It takes several years, depending on the soil thickness and drainage condition. Secondary consolidation happens after pore water pressure has dissipated. This occurs due to slow rearrangement and compression of clay particles over time. Both stages must be considered because they improve the long-term performance of embankments constructed on soft ground. The next is function of prefabricated vertical drainage PVD inserted into the soft clay layer. Their main purpose is to create artificial drainage path, allowing water inside the clay to travel as much shorter distance before exiting. So, instead of moving only upward, water can now move horizontally toward the drain and then vertically to the surface. This significantly accelerates primary consolidation, meaning the settle that would normally take years can occur within months. By speeding up drainage, PVD have achieved quicker improvement in strength and stability. Rule for preloading. Preloading is a technique where temporary load, such as additional fill, is placed on the ground before permanent construction. The preload applies pressure greater or equal to the expected service load of the highway embankment. This extra pressure squeezes out more water faster and forces most of the settlement to occur before the final structure is built. In some cases, just loading is used where the preload is slightly higher than the final design load, further reducing future settlement. Once consolidation is achieved, the preload is removed or trimmed to the design level. Interaction between PVD and preloading. Combination of PVD and preloading creates highly efficient ground improvement system. Preloading generates the driving force needed to push water out of the soil, while PVD provides drainage pathway so that water can escape faster. As pore water pressure drops, effective stress increases, resulting in reduced settlement and improved shear strength. This interaction allows consolidation to be completed in a controlled and predictable manner. The accelerated improvement means the construction can continue sooner with greater confidence in the performance of the embankment. Now for the importance of instrument. To ensure the ground improvement system is working as expected, engineers use geotechnical instruments. The settlement plate measures how much and how fast the ground surface settles over time. It gives engineers direct evidence of vertical movement. While piezometer is installed inside the clay layer to monitor pore water pressure. This tells engineers where the consolidation is progressing as planned. An inclinometer placed near the embankment slope. It detects any horizontal improvement, helping engineers identify potential instability before it becomes dangerous. By collecting accurate field data from this instrument, engineers can compare actual performance with predicted values. This allows adjustment when necessary, ensuring both safety and quality control through the project. Now, planning of the model that we're going to do. Okay, first, identify the geotechnical problem where the submarine clay excessive settlement, low shear strength, and slow consolidation. And then second one, we need to select improvement method where we decide to install PVD and reloading. Now, third step, decide model scale. We need to decide cross section showing soil layer, drainage, and instrument. And so for the first four steps is choose suitable materials with safe, durable, and realistic stimulation. Last but not least, the fifth step, which is we need to plan instrument method guided by BS 590 and ASTM. Instrument placement and purpose. The same thing that I explained earlier, where there on the table we have the instrument, which is settlement plate, piezometer, and inclinometer. There's location, what it measures, and why it's important. Model. Construction step. First we need to prepare a model base act as a soil, and then we need to put soft clay layer act as it was a soft clay, and then we need to add all the instrument PVD, piezometer, inclinometer, and everything. After that, then we construct the embankment. Act as the real what's the real on site. Lastly, demonstration mechanism. We engineer applies cage loading on the embankment In the model, this is shown by gradually adding sand layer to simulate construction loading. Then observe the settlement behavior. The ground surface lowers gradually and the settlement plate record this change over time. The model shows the pore water drainage part. Water flow horizontally towards the vertical drain, then vertically upward to the surface. This shortens the drainage distance and speed up the consolidation. Each instrument has specific role. Well, settlement plate measures surface settlement, piezometer tracks pore water pressure reduction, and inclinometer detects slope stability and lateral movement. Together, they provide reliable data so engineers can make safe information decisions. So, by combining stage loading with PVDs and monitoring instruments, engineers achieve faster consolidation, improved strength, and greater confidence in embankment stability. That's all for me. Thank you.
Hello, my name is Nesminjiri, daughter of Armugam. My registration number is 01BCT24F3030. Let's look at why PVD is essential for this project. Without PVD, the low permeability of the clay means water can take decades to escape. If we build too fast on this wet soil, the water pressure builds up, making the ground act like a liquid and also causing the slope to collapse. By installing PVDs, we provide a highway for the water to escape vertically. This dissipates pore pressure rapidly, strengthens the soil, and ensures that the settlement happens before we even open the road to public. Next is monitoring procedure and instrumentation. Our monitoring procedure is the eyes and ears of the engineering team. We don't just wait for the project to end, we monitor in real time. We use settlement plates for vertical movement, piezometer for internal water pressure, and inclinometer to check if the soil is pushing outward. By taking these readings at regular, disciplined intervals, we can build a complete profile of the ground's behavior. This allows us to adjust our construction phase based on how the soil is actually reacting, rather than just following a theoretical schedule. Next is interpretation of monitoring data. Interpreting the data is where engineering judgment comes in. In the early stages, we want to see rapid settlements. It proves the PVDs are working. As time goes on, we look for the settlement curve to flatten out, which tell us the soil is becoming dense and stable. However, we must be cautious. If our piezometer shows that water pressure isn't dropping, or if the inclinometer shows the ground is bulging sideways, it means we are loading the soil too fast and must stop immediately. Next is safety control and trigger levels. Safety control is managed through trigger levels. We have predefined limits for every instrument. If the settlement is too fast or the lateral movement exceeds our safety margin, we stop work instantly. We don't guess, we follow the data. This might mean pausing the loading for a week to allow the water to drain, or in extreme cases, remove some of the soil. We only proceed when the readings prove the ground is safe enough to handle the next stage of weight. Also, risk analysis and stage loading. The primary risk on this site is the low shear strength of the marine clay. To manage this, we use staged loading. Think of it like a gym workout. You don't lift 100 kg on the first day. We apply the small amount of soil, wait for the clay to get stronger through the consolidation, and then add more. This systematic approach combined with our instrumentation, ensures we never push the soil beyond its breaking point, preventing catastrophic ground failure. Moreover, engineering standards and practice. Our work is anchored in international and local standards. We follow the BS 5930 for our site investigations and ASTM standards to ensure our instruments are installed accurately. Since this is a Malaysian project, we strictly adhere to JKR and also ATJ guidelines. These standards ensure that our safety factors are high enough for our local tropical climate and soil conditions, providing a result that is both technically sound and illegally compliant. Then, the safety philosophy, which is the safe-fail approach. Our safety philosophy is simple. We treat the ground as a guilty party until proven innocent. We assume it is unstable until our data shows the water has left the soil and the clay has hardened. This proactive stance isn't just about protecting the project budget. It is about protecting the lives of the workers on site today and thousands of motorists who will use this highway in years to come. Additionally, sustainability and environmental impact. Sustainability is a major advantage of the PVD method. Traditionally, the engineers would dig out all the soft clay and replace it with the sand, a process that is expensive and terrible for the environment. By using PVDs, we improve the soil in place. This means fewer trucks on the roads, less fuel consumed, and much smaller carbon footprint. We are working with nature of the soil rather than trying to fight it, leading to a road that is cheaper to maintain over its 30-year lifespan. In conclusion, PVD with preloading is more than just a construction technique. It is a comprehensive safety and engineering system. It allows us to build fast and safely on ground that was once considered unbuildable. By following strict standards and listening to what our instruments tell us, we ensure an economical, sustainable, and most importantly, safe highway for the future. Thank you.